Hello again, chemistry. So, with this boiling point elevation or freezing point depression, how do we make any calculations with this? So, in your homework here, we have the question, predict the boiling point of a 0.2 molal solution of glucose in water. So, it matters what our solvent is. It also matters what our solute is. Because of this concentration. We'll see this again in the next little problem here. So boiling point, we have two equations in this section. We have this one, and we have the one for freezing point depression on the page before. So since they asked for boiling point elevation, let's use that one and our equation. I'm just going to write it down here. Delta T, which stands for change in temperature. And this is talking about B, that B stands for the boiling point, whereas the other one has an F on it, which is standing for freezing point, equals K. Now this K stands for a constant, and it is the boiling point constant for water. And we can look that up in your book. It's nicely here on the bottom of the page. And for other substances, it's in a table on the page before, which you may have to reference when it comes to other substances: acetic acid, camphor, ether, naphthalene, phenol, and water. We're going to do water, which is, for boiling point, is 0.51. So here we have our equation, and what do I need to know to predict the boiling point? Well, this is only the change in temperature, so I don't know that. That's what I'm trying to figure out. K, I know that, so I know my K equals 0.51, and that's degrees C per molal. And the molality, I also know, is 0.200. How many sig figs? 2 here and 3 there. So then all I have to do is plug in my numbers, and I put delta T will equal 0.51 degrees C per molal times 0.200 molal concentration. Notice that the m's are going to cancel because we're going to want to have the degrees left. So our delta T will equal, if you put this in your calculator, you will find 0.2 times 0.15. So a half of 0.2 would be 0.102 degrees Celsius. That's not very much, but it's not very concentrated either. So, but is that the boiling point? Is my boiling point now 0.01 degrees? I'm sorry, 0.102 degrees Celsius? No. I have to remember that I take the normal boiling point for water, in this case 100 degrees Celsius, and I have to add the 0.102 to that, and I get 100.102 degrees Celsius. So that's what we're going to put up here, 100.102 degrees Celsius. Now, one little technicality here is, you say, well, we got 3 sig figs here. How did we wind up with 6? Well, 100 is our definite boiling point. It's 100.000 forever. So we can add this to this, and it's about how many places after the decimal. So we're okay on this one. All right, now, what about predicting the boiling point of a molar solution of potassium iodide? Should we get the same answer? They're both the same concentration. Well, the catch here is that potassium iodide will split and form potassium ions plus iodide ions. So for every one you get here, well, you get two pieces here, making two altogether. So really, the concentration is not 0.2 molar. It's double that as far as the number of pieces. That's what a colligative property is. So we would do all that same calculation, except for when we get to the change. Instead of, we could put a 4 here, or we could just take the 0.102 and we can double it. So 0.102 degrees Celsius times 2 would equal 0.204. Add that to the 100 plus 0.204, and you get 100.204 degrees. And that's what we're going to write over here, is 100.204 degrees C. That's the new boiling point. We had to have the change, add it to the original boiling point to get the ending new boiling point. That's when the water will boil. Now, let's take a quick peek at the next one. And the chief ingredient for antifreeze is ethylene glycol. Assume that the ethylene glycol is added to a car radiator that's holding 5 kilograms of water. Well, how many moles of ethylene glycol should be added to the radiator to lower the freezing point of the water from 0 to minus 18 degrees? Well, the first thing we have to figure out is, okay, how many moles do I need to change at 18 degrees? We use the same fancy equation of delta T. This time we're going to use freezing point equals the constant of the freezing point, in this case of water, and the mole concentration. Well, they didn't tell us what the concentration is. That's what we've got to figure out. So we've got to algebraically rearrange this equation and get the K on this side. How do we get the K on this side? Why, we divide by K. So it's going to end up being the mole concentration, which is what we're going to have to figure out here, is the change in temperature divided by the freezing point, the constant for water. Well, what's the change in temperature? It's minus 18 degrees Celsius. And what's the freezing point constant? It's minus 1.86 degrees, which we get from the page before in our book or that table. Okay, so when we do that calculation, we find that it is 9.677 moles per kilogram. Now, that's how many moles you would need in 1 kilogram. But they said how many kilograms? 5 kilograms. So how many moles will I need to get 5 kilograms of water to change by 18 degrees? I will need 5 times that amount. So I'm going to take that times 5 kilograms. Notice what's going to happen to my units. They'll cancel, and that'll tell me how many moles. So I go that times 5, and it comes out to be 48 moles. And that's exactly what goes up here. Then, well, since I don't know how to measure moles into my radiator, I need to convert those moles to grams. How many grams? Well, I'm going to take that 48 that we just figured out, 48 moles of ethylene glycol, and that's C2H4, and we're going to say that, well, how many moles, how many grams are there in 1 mole? If you take the periodic table, add up all these elements, you'll find that it is 62.08 and we're not going to take the time to do that right now. So then it's just cancel, cancel, left with grams, do the math in your calculator, and you get 2.978 times 10 to the third grams. Well, how many sig figs? Well, we started with 2, got 4 here, so to reduce it down, this kind of kicks them all up, and we get to be 3.0 times 10 to the third grams. Now, grams, we could have moved the decimal 3 places, and this would be just simply 3 kilograms. We would need 3 kilograms of ethylene glycol. And then for section or question C, ethylene glycol has a density of 1.1 kilograms per liter. How many liters of this should be added? Well, another little conversion factor. We're just going to take the 3 kilograms. Just watch for conversion factors. There it is. So if I want to convert kilograms to liters, where should the 1.1 go? Well, that's got the kilograms attached, so I go 1.1 kilograms in 1 liter, and then I do the calculation, and we come up with 2.7 liters. Oh, I've kind of skipped over turning this to kilograms, but you can do the conversion by moving the decimal 3 places. All right, well, that kind of concludes it for the calculations. Watch out for this, I would call going forward, and this example is kind of going backwards. So as you continue your homework, watch for the going backwards and forwards in doing your calculations.